What's up, everyone? Today we're going to talk about convex and non-convex Lyapunov functions to prove stability for a given linear differential equation and linear switch and switching signal type of signal systems. And we're going to be analyzing a paper that whose description is given in the description section below. And this is going to be a comprehensive review, but there are going to be probably more videos about the algorithmic and then optimization part of the work, and we'll be talking about okay, what do I mean by that. So let's start with the simple definition. Before saying anything, this is the system that we are looking at here. Instead of saying like convex hole, we have that bar on top of that CO expression, and that implies we're going to take the convex hole and closure. All right, so okay, that's one thing to keep that in mind. We have m functions on the right hand side, and once again, this is a set. For each t, x dot, the vector field, takes a value from this set. And we're going to be looking at proving the stability for that type of system. And again, this is like a very general expression, like we are not like imposing any type of structural constraints, and yeah, we are going to keep it as general as possible. After a while, we're going to impose some structure, and then we will look at the structure of the Lyapunov function, and then look at the typical stability conditions and try to express the problem in a way that is only an optimization for the parameters of the Lyapunov function. Okay, so let's continue. Here, this is like the first definition, and it says that for the system 1, which is this system, okay, where each of them has the same equilibrium point, and then again, this is an assumption, each of them has one equilibrium point, like one solution, or 1, 0, and which is 0 in this case, to simplify the like operations we'll be conducting. And okay, this is saying 0 is yes for system is asymptotically stable as if, okay, there are two conditions. First, stability. This is what we are familiar with at this point, like the typical expression for all epsilon positive, there exists delta, and which depends on epsilon, such that x0, like initial point, when it is bounded by, the magnitude of it is bounded by delta, implies, let me wait a second, let me get another like that. Yes, yeah, okay. All right, for all t. Okay, this is the stability ISF in sense of Lyapunov condition, and okay, this is what we are familiar with already, and this is the attractivity condition. What does it say? It says that there exists m such that for every solution which is inside this, let's say m ball, goes to the origin. Yes, okay, and then this is attractivity. So when we have two of them together, it gives us asymptotic stability. And here, if m goes to like infinity or something, like whole region Rn, right? Then we have GAS, global asymptotic stable system, on our hands. So let's continue. It is well known that asymptotic stability can be proved via Lyapunov-based techniques. We are familiar with this notion. So in this paper, they're talking about the functions that are not everywhere differentiable. Like these type of functions are, there needs to be some additional care, right? And it needs to be there. So we need the following notion of generalized gradients. Now, this is another type of gradient notion that we're going to be looking at. And let's look at the second definition here. First of all, we have this like locally Lipschitz continuous function, and then we know what that is. This Rn u function is defined from Rn to R. Okay, like typical V, like Lyapunov function, for example, right? This is the type of function that, yeah, we used before. So the generalized directional derivative expression of u at x along V. Alright. So when we have f of x, for example, right, and we would look at the derivative of this function for x naught, like specific point. And here we need a point plus a direction. Okay, and this is the direction. If I'm not gonna dwell on this, this is like, yeah, this is not, you know, this is not the part that I wanna spend like too much time. And okay, this is the general directional derivative, and then here, after defining that, we have this zeta, and it belongs to the generalized gradient. Okay, so after computing that, we have this expression, and for all like zeta terms, and we have subgradients. And then, okay, let's try to kind of simplify this. So let's imagine we have this function. All right. For a second, let's stop and think about what would happen if we have like an f function defined from Rn, or no, not Rn, just R, like reals to reals, right? If we had that, this would be our notion of derivative. Okay, we're familiar with this. And if x is defined on like Rn, we wouldn't be able to write something like that. And then what we do, we would write it in that fashion, right? Okay, got it. So this lambda expression would be our quote-unquote derivative, right? Like differential. So sub differential, basically, we have, instead of inequality, we have inequality, right? And then for all the lambda terms that satisfy this type of condition, and the set that composes all those lambda terms is our subdifferential or Clark derivative, and or Clark differential. And for example, we have the absolute value of x, right? Okay. When we have something like that, so basically, at this point, I mean at those points, okay, we know what the derivative is. It's a straight because it is continuous, like, or rather, it is differentiable, right? However, at this point, what is the derivative, right? And basically, our derivative is this. No, or like how would we define the derivative? Derivative is not a like, for example, for this point, our derivative is this, right? Okay. However, for those points, like for that specific point, we have not a single volume, right? But a set of values. So we have a set. So that is the basic. And then such that, for example, so we have all those, let's say, tangent planes can be drawn by this, like that. Okay, got it. Imagine something like that. Yeah, and then you can imagine that this is, since we said that there was absolute value, it would take values between -1 and then +1, right? Okay, got it. Yeah. Let's say this is the f of x, something like that. All right. So yeah, let's look at the lemma and suppose that there exists a local Lipschitz function. Again, instead of saying like continuous differentiable or something. Now we are looking at a more general case. Here in this case is being local Lipschitz function and a class K function. We know what that is, like we have a separate video about it. And okay, we need to look at those constraints. There are three. And this one is, we are familiar with, 0. It takes value 0 when it isn't 0, or rather equilibrium point, and it needs to be positive definite. And usually what we would have v dots, right, being negative definite, right? Here's the thing, like what is v dot in this case, right? And that's not, it's something we can write it directly, because there are cases that this is not differentiable. Okay, and when you cannot take the differential, basically you need to look at the sub differential, right? This set basically, and then here we don't have one value. Like for a given x, we do not have, like remember that, like always remember absolute value of x, for example, right? We would have a set of, like set of values instead of one. Okay, but here's the thing, since we have set of values, then which one we need to look at. But basically what I'm saying is that v dot is not, v dot of x is not a single value, it's a set of value, right? And then we had less than 0, like negativity, some type of negativity, right? And type of constraints, like we had something like that before. And now, since we are saying that, imagine the problem was, hey, v dot is, it's not a single value, but it's a set of values. I mean, you can imagine in this case, we would need to look at the worst case, right? Worst meaning, like we want this to be negative definite, and then worst meaning like the maximum, right? If the maximum, if we can guarantee that the maximum, imagine this takes values, like for any given x, it takes values from a set of values, we would look at the maximum one, and if we can show that the maximum satisfies the negativity condition here we are trying to impose, then we could conclude the stability. All right, now this is basically what we have. So this is, like if you remember v dots, we would write something like this, right? Okay, sorry, yes, and then which can be written something like that. Yeah, that is literally the thing. Instead of saying that, we are saying zeta. Okay. All right. And this is a k function. By the way, here's some small thing to point that out. This is from Rn, right? This is from Rn to R. So this should be norm, but this is notation of this paper. Yeah, like don't think this is like an absolute value or this is like a scale or something. This is norm. Yeah. And okay, then the origin of the system is asymptotically stable. All right, we got that. And V is called a Lyapunov function, okay, for the given differential inclusion. If in addition V is, like again, like similar type of constraints, radially unbounded, which is the definition of a function being radially unbounded, then the system is equivalent asymptotically stable. All right, let's continue. And here's the thing. Now, like since we discussed in the previous video that there are systems that are stable, like asymptotically stable, I mean, and or even like a global asymptotically stable. However, we cannot, like we establish the type of cases, the type of scenarios, and then the conditions that would prevent us from finding, it would be impossible to find a convex Lyapunov function. However, the system is asymptotically stable, right? And in this case, we would need to look at, like we would need to enlarge our Lyapunov function parameterization or the type of functions that we would consider. Like usually, so far, for example, we would look at a quadratic function in this case, right? And that is all right for many cases. However, now we are in the big boy leagues, right? And now we need to look at other type of Lyapunov functions, right? And complicated systems require more like basically the same, I don't know, like complicated Lyapunov functions to prove stability. All right. If I said it in a better way, that would be like a Spider-Man quote. But anyway, so harder systems. Wait a sec. I'm thinking, what was the original quote from Spider-Man? A great power comes with great responsibility. Okay, yeah. I don't know, like nonlinear systems comes with harder Lyapunov or more complicated Lyapunov structure or something. Anyway, all right, that was a tangent. So now, given k functions, here we are defining some type of non-convex. We will talk about why that is not convex. Some type of Lyapunov function. All right, where each of them, instead of defining one Lyapunov function, or rather, okay, let's go through the definition like one by one. First, we have k functions. All right, but do not think immediately this is going to be the Lyapunov function. Just like starting from v1 dot 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 vk, where each of those functions, they're from the set. What does that mean? It is a set of functions from Rn to R, okay, and math cal 1. What does that mean? It means that like you need to take the derivative this amount of time, right? This many times. Here 1, and since we have c, that indicates the function being continuous. All right. You have a function, you take the derivative, and then what you have, the derivative of it, is if it is continuous, then okay, it is from the set. Yes. Or another way of, or maybe like a simpler way of saying it would be continuously differentiable. All right. If that was 2, for example, we would say twice continuously differentiable. All right. And simple thing to point it out, but okay, we will be looking at it more and more. We define a MaxMin function, and this is the notation. All right. And here, this is the structure that we have. So when you look at it the first time, it might look kind of weird, but we're going to talk about what that is. Basically, you have a max here. Let's consider like a big area, and then what we have, let's imagine it says that we need to have like some type of capital J. Let's say this is 3. Okay, so min of, let's say, S1, S2. Let me get another color. Min of, let's say, S3, S4, S5. Okay, I butchered that S5. All right, let me get another color. Green is nice. And is, let's say, S6, S7, S10, for example. Yeah. Okay. Here, what you do? Why did I say S? Okay, scratch that. Instead of S, we have V, V1, V2, V3, V4, V5, V6, V7, V10. Okay. For any given X, right, you basically solve this problem, right? Like when I say V1, I mean V1 of X, right? For any given X, you basically look at which one is minimum. Let's say this is V1, which one is minimum? Let's say V4, which one is minimum? Let's say V8. And then you ask the question, which one is max among those 3 functions? Let's say V8, and then you basically return this one as the answer. For that given, let's say this is X tilde, right? For any given X tilde, you return, you compute, and then you return that value. All right. So this is the procedure by which you compute this MaxMin function. Okay, and you have J subsets, you have K functions, and each, like S sub J, takes values from this set, right? So they're basically J subsets. Like you need to have, like, for example, we have 1, 2, and then 3, right? You need to have J number of min expressions, okay, inside that max here. Okay, and then there are K, let's say, functions, v1 dot vk, basically functions. Yeah, that's it. So this was the definition, MaxMin function. I mean, I don't even need to point it out, but this is not convex function, all right? Okay, let's continue. Here, given a function, for first of all, this is when you have you need to give me kv functions, like v1 dot vk, k continuous differentiable functions, and then the moment that you define them, you have a set of functions, right? This is like a set of functions. Okay, so v is a MaxMin function, and then probably the correct way of saying is defined by those like basis functions. All right, and now let's move on. We can construct a map alpha v here, and here I think this is a nice thing to point it out, and this is not a like notation error or something. We have two errors, right? And usually we are familiar with f of x, for example. This is a function. Let's say it takes values from Rn to R, right? How we would write it? We would say Rn to R with only one arrows, right? And this is when you have two values. When you have two values, that means it returns a set such that that set is included, or that set is a subset of this specified, like this set. Okay, makes sense? Yeah. For example, like alpha x, like let's say I say alpha x, and then x is in Rn, and then we set that from 1 dot k. The answer might be, surprise you, no, x bar, the answer might be, for example, 1, 3, and then 5. Again, this is not a number, this is a set, right? This is a set of values. Okay, and which shouldn't surprise you, because for any given x, and then the type of functions that we're looking at, we can have more than one functions that to think about. Okay, let's put it that way, and let's continue. So this is the definition, and I think this is essentially in the active map or something. That was the, yeah. Okay, let's look at this alpha v function. This is a set valued function or map. Okay, so here's the definition. L, okay, such that for all neighborhood u of x, first of all, you give me a x, and then I will look at all the neighborhood of this point such that there exists an open subset of this neighborhood such that how can I say, okay, let's say this is x, all right, and then let's say this is the neighborhood. Okay, and then we're going to have some, and then what is it? This is u. All right, let me get the this color. Then we're going to have an open subset of this neighborhood, all right, such that inside it is the what is the correct expression? Inside it is only, or rather, yeah, only one V is active. Make sense? Yeah, I think that would be a correct way of saying it. Okay, so you have this neighborhood, and then you have a open subset, all right, such that like we have this L. Let me get this color. Actually, now that I think about it, like our, let's say V1, like this place is, for example, where V1 is defined, and then let me get another color, and this place is, okay, rather, yeah, here in this place we have V2. Okay, so first of all, so we are not saying this place is the domain, I think the correct expression, and is only in the domain of V1, or is only in the domain of one function among those like basic functions. We are not saying that. You give me an L, and then I will check if it is in the domain. Okay, you give me an L, like let's say V1, and then I will look at if all the points, like all the points here, would be mapped to okay, this is going to be hard. Wait a sec. Okay, first of all, let's remember, like we have a v of c, like we have a v function. What is the, let's say max, right? And then you have min expressions, like v1, v2, and then let's say v3. Okay. For a given x, this alpha v of x tells you this is a set volute map, let's say 1 and 3, or rather 1 and 2, for example, right? I mean, it wouldn't be possible, but yeah, let's say that is the case. Okay, 1 and 3. Okay, so here's the thing. When we have that situation, what are we saying? We are saying that V1 and, or rather, V1 and V3 is active, right? Yeah, let's have this lingo. Okay, that would be healthier. Okay, so let's start from the beginning. Literally the beginning. Okay, it's always, smart to do that. When you find yourself confused, just start from the beginning. You give me an x, right? Okay, and then at this point, I will look at, like we have functions from 1 to k, right? Okay, like these are the indices. I will look at all the indices, like one by one. Like, okay, let's look at 1, for example, like L index, and I am looking at, for all neighborhood u of x here, and then I am looking at, there exists an open subset of this neighborhood, all right, such that we have this condition. Okay, VL is active in this set. All right, if you have that, if that is the case, then you add that to your output. Let's say that was 1. Okay, and then you continue like that. Okay, we look at index number 1, then you look at index number 2, dot dot dot, and then when you find an index that satisfies that condition, then you add it and then you return it. Okay, so this is the method by which you would compute the output of alpha v of x for a given x, of course. All right, so okay, let's look at intuitively the set valued map alpha v captures the fact that every point is surrounded by regions where the function v is continuously differentiable. Okay, that makes sense, right? Okay, why? Like for a given x, right? We are basically saying that like this condition is for that all the points, like when we look at those points, we are basically saying that VL is active. Okay, what does that mean? We are not in the boundary or something, and VL is active. So in that region, VL can be differentiable. Okay, I hope you can see that. And yeah, V is continuous differentiable and equal to V sub L for some L. As an example, consider, yes, this type of function. All right, and then let's look at the simplest case, V of x, which leads to, yes, that's when alpha v, I think this is also another issue, when alpha v of x is not a singleton, when, okay, let's imagine like we have v1 and then we have v2, right? Okay, and then let's imagine we have we are looking at R2 is our state space, and let me get this color. Yes, say that, okay, this part is the part v1 is active, and then let me get the green, and then here this part is where v2 is active. All right, and then let me get another color. That part, like this basic boundary, and then this is the keyword here, this boundary is switching or like some discontinuity taking place, right? We need to have some special care like for that, let's say, set, and interior of those points, when you look at those like interior of those like, blue and green region, alpha v for those, let's say, regions would be a singleton, either 1 or 2. But for those boundary points, then you would have something not a singleton, right? And we can also, another situation, for example, let me get, yeah, let's imagine that was the case. Yeah, let me get another color, green, no, red, yeah, red is, all right. Okay, here, look at this. I think green. Let me make it black. Okay, here, for this point, we need to have, let's say this is V3. We need to have like 1, 2, 3, right? Okay. At this point, only at this point, 3 functions like V1, V2, and V3, like all of them, like 3 of them would be active. This is basically what we are saying here. Okay, this is like the notation. All right. All right, let's continue. Yeah, this was like some sketch. Okay, so this is the first theorem. Consider the differential equation that we, expressed before, and given k positive definite functions, of course, it would make sense to have those like quote-unquote base functions as being positive definite functions, right? Okay, and then okay, a continuous differential from Rn to R. Consider a MaxMin function here, where you have like v1 to vk as being basis functions for that given specific function class. If there exists a class k function, again, like this gamma function, like we are familiar with this type of notation, and for all x and for all I, right? What does that signify is that, okay, let's remember what that m was. Let's say x dot n convex half. Yeah, that was it. Yes, that is what we have. All right. So we have m functions coming from, let's say, dynamics, and then we have k functions coming from the Lyapunov function, let's say structure. Yeah, and so basically the stability definition is adapted to this new case where you need to look at all those Lyapunov functions, and then you need to look at all those, let's say, subsystems, right? Here, yeah, from 1 to m. Okay, and let's keep on going. Again, we have like class k function. This is norm. That is it. Instead of, okay, let's remember what, for example, if we had something like that, right, like the typical function, and then the, let's say this is dynamic, and then this is the Lyapunov function. What would be our constraints on this Lyapunov function? That being positive, and then v dot, and then how would we write v dot? We would write it's gradient of v transpose f, right? Negative. This is and then when we say negative, right, like negative being negative definite, and this is another way of like cooler, quote unquote, a cooler or more professional way of, more generalized way of writing that negative definiteness property. Okay, here we have, due to our Lyapunov function definition, now we have basis functions, and then we need to consider those basis functions. And for each given x, there are some basis functions are active, right? Okay, for example, let's say we have two basis functions. Here, this is base where basis function 1 is active, and then here, basis function for Lyapunov function we are talking about. Okay, sorry for this mistake. All right, here, second one is active. Basically, we need to look at every point one by one, right? And okay, we need to look at every point, and for a given x, we need to determine which Lyapunov function is active, and then if for a given x alpha v is singleton, then we would be able to compute the gradient, because why that is the case? If it is singleton, if alpha v is singleton, then, and the output is L, then v of x, which would equal to v sub L x, is differentiable. In this case, we would be able to find the compute the gradients. Okay. And then we also need to look at, for a given x, we also need to look at which subsystems are active. Yeah, that is it. We are only considering those cases. Like now, we have, for any given x, we first look at which subsystems are active, and then due to the construction of our Lyapunov system, or Lyapunov function, we also look at which let's say, basis functions are active, right? We consider them. That is it. So basically, there are two for loops, right? This basically tells us that. Yeah. And okay. And if that is the case, then we have asymptotic stability. And if each one of like Vj and each one of those basis functions is really unbounded, then we would have global asymptotic stable system. All right, linear case for the linear differential equation. Now, here, before that, we had Fi, right? So now we are putting some structure. We are making our life basically easier in a way. And again, the reason why they wrote like AI times x, because this is vector field. Okay, got it. All right, again the convex hull, and we have subsystems from a1 dot 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 am. We can restrict our search for a Lyapunov function with degree of homogeneity to. What does that mean? Okay, here let's say you have function x. Okay, and then you look at f of lambda x. Right, if you can write, let's say, n lambda to the n times f of x, then you can say that f of x is the homogeneous function with degree n. Yeah, that is it. And then there are some like algebraic simplification that would help us to figure out the parameters of the Lyapunov function, right? Because we have a Lyapunov function, and then it is, although we are trying to put some structure, we need to make it as, instead of like really general, we are trying to find a special structure where we can parameterize it, and after that we will need to continue our, let's say, analysis procedure where we define a set of constraints from those general Lyapunov function constraints, and then in the final stage we will try to impose hopefully manageable constraints on each of those Lyapunov function parameters, and we will turn that into whole like expression into a optimization problem. Hopefully it will be something we will be able to solve. Yeah, like that is, again, I am highlighting that point many times. I understand that it might get boring, I understand that, but this is we are looking at all those like definitions like lemmas, proposals, etc. But it would be smart to look at our like objective, right? Why are we doing this? Yeah. And all right, and thus why are you watching my videos, like, for example? Okay, this is like a good question to ask yourself. All right, and thus we can consider the MaxMin function obtained from quadratic forms. And when we say quadratic forms, we mean basically something like that. Yeah, that type of like forms, we say quadratic forms. And here, like before that, MaxMin function, when we say MaxMin type of function, we had k basis functions, v1, vk, where each of them would be continuously differentiable, right? Okay, and here again, each of those v1 or v sub j functions, we are not putting any constraint. It can be quite general if you can imagine. However, since we are looking at a specialized differential equation, which is like the LDI, and we are saying that, okay, let's try to have, instead of having a really general Lyapunov function definition, let's look at a special structure, even more special, right? Okay, like MaxMin functions, like, okay, it was like the first step, and then in the second step, okay, we're making it even more general. Like, all right, Okay, MaxMin of quadratics basically is the structure that we are going to be looking at. All right. Again, instead of saying like v1 dot dot dots, now we are, instead of vi, we will have pi basically. All right. Again, everything is the same. Here, yeah, this is the notation. K, for example, let's say S3 is all the sets of, like all the permutations of 1, 2, 3. Okay. Basically, it means that. And then, what is the number of permutations that you would have from 1 to 3? Basically, 3 factorial, right? Which would be 6. Okay. Let's try to write them down. 1, 1, 2, 2, 3, 3. Okay. 2, 3, 3, 2. It would be smart to regroup them. And 1, 3, 3, 1. And 1, 2, 2, 1. Okay, so there, yeah, we have 6 of them. All right. So Sk is the set of all permutations, possible permutations of k elements. All right, from 1 dot 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 k. Okay, this set is what we're going to be using in a moment. We note that when we have k quadratics, we can partition. Yeah, this is important. All right. Let me say a few words on this matter. Okay. So let's try to make it simple. S3, right? What? Actually, I should maybe. Yeah, okay. Let's say we have P1, P2, and then P3. And using those quadratic forms, we define our Lyapunov function. Okay. And here's the situation. For each of them, each of them corresponds to a region in the state space, right? Okay. And here's the special thing about that. Let's say 6, right? 1, 2, 3, 4, 5, 6. Yes. This definition is, or rather this partitioning of the state space is useful. Why? Because each one of them corresponds to a region in the state space, and then each of those, and then this C row, for example, right? Like C row 1 dot dot dots, and this make the union of them. C row 6. Here it is R2, like all state space. In addition to that, there's another point to highlight, but okay, I will be highlighting that later. Okay, can partition the state space Rn as union of symmetric cones. All right. Okay, so when we say row, like for example, when let's look at 2, 1, 3. When we say 2, 1, 3, what do we mean by that? We basically mean that 2, right? Okay, P2. All right. P1. And then P3. If we, for a given x, let me get this, yeah. For a given x, you give me an x, and if that is what we have, then we say that, let's say we are in this part, like subset of the state space. Make sense? Okay, got it. That's it. Look at from J1 to JK, and then J1 to JK. Yes. We are partitioning. Here's the reason why we are doing this. Why we are defining, this set of permutations, all possible permutations, set of like quadratic functions, like MaxMin structure, symmetric cones, etc. We are doing it to be able to partition the state space. Okay. Additionally, it is observed that the map alpha v is constant in the interior of C row. Okay, which kind of makes sense. Like, for any given row, for any given x, rather, wait a sec. Yeah, for any given x, first of all, what you do is you look at those cases and then you determine which one is active. The only one needs to be active, and then except the boundaries and stuff, and then C row 2, for example, right? Okay. It is observed that the map alpha v is constant. Yes, alpha v would be constant in the interior, which kind of makes sense. Like, in the interior of that region, let's say that corresponds to that. That holds in the interior. Because of that, alpha v of x in the interior of one of those regions would be constant. Okay. Alright. By the way, these are, like, let me tell you, I understand each one of them, when you decompose it, it sounds like an easy concept, but when you, like almost like Lego blocks and stuff, and when you basically put them like on top of each other, it's almost like notes, like music notes and stuff. And each one of them may look simple, but when you get them, all of them together, it becomes something like much complicated and much more helpful too. All right, here's the corollary, and consider the system. Right, the system is AFDI type of system, and the function v. I mean, we know what type of function it is. We have m functions from m subfunctions. M subsystems, and then k basis functions for k quadrics. Okay. Right. And then if for each subsystem and for each row gives you a part of the, or partition, some part of the state space. All right. For each subsystem and for each part of the subsystem region in the state space, if there exists a set of constants, positive constants such that this inequality holds, then the system is covalently stable. Okay. Let's try to understand that. First of all, what does it say? For each. It says for each I, and for each row, right? I, again, we know what I is. I takes values from 1 ... m. For each subsystem, and then for each any given permutation, it basically corresponds to a region, like subregion or subset of the state space, basically. Okay. And all right. And then again, we basically have v dot or something similar to v dot, right? And since we need to look at for any given region, we determine that in the interior of given row, like C row regions, in the interior of C row regions, alpha v would be constant. We know that is the case. And from that, we determine which Lyapunov function is active, or which Lyapunov functions are active, and then which subsystems. Actually, wait a sec. No, wait a sec. This is, I'm not talking about switch system. This is, linear differential inclusion. So is for each I, yeah, exactly. This is not like for a given X, you need to look at each subsystem and then see which one is active. No, wait a sec. We are looking at convex all of them. So for any given X, all of the subsystems, like all of the subsystems are active. So yeah, excuse my notation here. I think that kind of got me confused. All right. So for any given, let me take it from the beginning, and for any given row, you tell me like the C row. What is it? It is a subset, some subset of state space. Okay, and we know that in that subset of the state space, alpha v, which tells us which Lyapunov functions are active, and you compute that which Lyapunov functions are active, and then you look at this inequality. Okay, you are trying to, for given, by the way, like here's the thing, for given p terms, like here we are basically looking at, this is not basically a analysis problem. I wouldn't want to say synthesis, but in a way this is some type of analysis problem, like half analysis or something, because here you are checking if a given like set of like p 1 dot 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 pk basis functions, quadratics, and so 50% of the job is done. You are looking at if it would be possible for you to compute a construct, a Lyapunov function using those given k quadratics. Yeah, this corollary basically allows you to do that. I'm going to give you p1 dot 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 pk quadratics, or matrices from which you can construct the quadratics and then construct a special MaxMin type of Lyapunov function, and if you can satisfy those conditions, like in LMI conditions, then you can come and state that these basis functions would allow us to construct as such Lyapunov function, basically. Okay, got it. Here's the situation. In the previous like section of this video, where we were looking at, instead of a sub I times x, where we had fi, we need to have additional constraints to be able to come and state global stability, to be able to claim that. Here, since our system is like more structured compared to fi, and when we satisfy those conditions, we can directly state that global asymmetric stability, which is kind of nice. All right. Okay. Let's move on. Yeah, this is basically the summary of what I just said. And comparison of max construction with other resources. Yeah, here's the thing. Like when we say MaxMin, right? And there might be some, we're going to have like max in the other. Yeah, okay, and then parentheses, and then inside say a set of set of, or we would have like a set of subsets, right, of 1 dot 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 k indices. Okay, and for the case where we have only 3 basis functions, then basically there's some combinations that you can do, right? Like for example, you can do P1, or rather you can do something like this, or you can do, for example, I mean, you can even do this, right? Because if you think about it, like instead of P1, I can say just minimum of P1, and then there's only one option, and then that comes out as this. And for example, like we can also have, for example, max min P1, P2, min P2, P3, and then min the move between P1 and P3. Okay, so there are like a couple different max min structures that you would have. Okay, got it. It all depends on the subset, your subsets, right? All depends on your j value and then s1 dot 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 sj, like those subsets. That's it. Okay, so here's the situation. This is lemma. So when you have those two LMIs, so this LMI lets you, let's say you have like a set of LMIs, right? And this LMI, and then there's one more LMI that we're going to be looking at. It helps you reduce those LMI constraints. Instead of like having 10 LMI constraints, it would be better to have like, let's say 4, right? So this is, what we're looking at here. Because here's the thing. And if you look at the structure of the Lyapunov function, and if you look at the, for example, where was it? Those type of constraints, these are not like, this is not polynomial type of algorithms that we're talking about at this point. We have factorial expression. So these are NPR problems. They are for, let's say, low order systems. Only you can have any hope of solving them, right? Okay. Additionally, like here we said that for given P1 dot 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 Pk, and what if no one gives me? What if I don't have any friends who would give me the basis functions for a Lyapunov function that I would like to construct to prove a stability for a given system? Then what would we have? What would we do? What would Lyapunov do in this situation? Like a control engineer would need to ask himself or herself. So we have a constant, and then again, let's say in this situation we don't know them, then unknown times unknown. Oh, what you have is a basically in this situation, I wouldn't want to say like basic non-linear optimization and then scare everyone, and I'm assuming everyone is already scared at this point, but this is BMI, right? So not that bad, not great, but there's hope. All right, like Aragon said in Lord of the Rings. Okay, and when you have those two LMIs, instead of having them, you can basically scratch them, and then instead of them, those two LMIs, you can write only one LMI. That is it. And here's the situation, like here's the important thing. I'm not saying that, hey, get rid of those like two LMIs and then just write one LMI. But this is a sufficient condition. If we have that situation, then it would be a sufficient condition. The moment that you say a sufficient condition, that means that you need to account for the conservatism that you're introducing to the whole system, whole problem, right? Okay, see, anytime you have like if and only if condition, that you are not losing, like quote unquote losing anything. You are not like, introducing any type of conservatism. And yeah, that's basically it. Okay, let me look at this, and then all right, now we will like prove it. It's like a very simple proof. Okay. Bless me, I guess. So yeah, here's the proof. Again, I, instead of writing P or what's it, P times A plus PA transpose, I basically wrote that. Okay, so I basically wrote what we have as a condition 1 and then condition 2, and then, and wait a sec, we are not trying to prove that, right? The proof is very simple, and then we will be looking at it. However, okay, let me say one thing. I'm thinking about it. Yeah, this is like the basic. This is, yeah, the reason why I wrote that. Anytime you have those two elements where you have this, the given structure, what is that? Like you have 2, 1, and then anytime I say like 2, 1, like P sub 2, 1, I mean P2 minus P1, like this is like a shorthand notation, alright, which you can kind of understand that. And then in the outer part, they need to agree the indices, and then when you have that situation, and again for like 2 of them should be the case, again like 1 and then 1, like indices agree, and then you take like the inner indices, and then you get P here 3 and then 1. Okay, you may not understand what I'm doing. This is not like a mathematical thing. I'm just like saying, if you wanna write it in a fast way, this is what you would do, and then you would write that P31, and again the outer indices agree, which is 1, and then you would get from 3, 1, 2, 3, 2. Okay, when you have those two concepts, of course, like this first term need to be same, and then, all right, two conditions, you, instead of looking at two elements, you can write something like that. And again, those lambda 1, and then instead of saying like tall values, lambda 1 and lambda 2, they need to be non-negative. All right, here, yes, again, this for final. Okay, there exists terms here, right, such that the given LMI holds. Okay, and then second condition, there exists constants such that this given LMI holds. Yeah, instead of looking at two LMIs, two LMI conditions, you look at one. That is it. All right, here this is like the end symbol. All right. Okay, let's keep on going. Here, this is mid of 3 quadratics. I mean, this is not naming that the author gave. And when we have 3, yeah, when we have 3 quadratics, basically this system or this structure is being called mid of 3 quadratics in this paper. Okay, and then there are some points being made. When you have this structure, the constraints that you would like to impose on the system are given by this. Okay, first of all, why do we have like this? Is that the equation number? Of course no. It's like it would be crazy to have equation number 321 or something. It would be, I mean, in a paper, of course, like it would be crazy. Even in the dissertation, it would be kind of weird or wild. Okay, so as you can imagine, these are the permutations of 1, 2, 3, right? And when you have permutations from 1 dot 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 to k, you would have k factorial terms. And then when we have like from 1 to 3, we would have 3 factorial, which is 6. 1, 2, 3, 4, 5, 6. Okay, got it. Okay, and these are the conditions, and you write those conditions. Okay, these conditions are direct result of the structure of the view upon a function. Okay, and then here you may be thinking, oh, we have only 6 LMI conditions, that's not bad. Wait a sec, no, you are wrong. We have 6 times, let's say, M subsystems. We would have 6M. We would have 6M conditions. Alright. That's it. And it says that I think that is like the worst. Yeah, this is the worst case. And in this case, we don't have any hope of like reducing the LMI constraints. I think that's, yeah. But that's not the situation like in Quasimax, and then that expression or designates this structure. Okay. Again, this is set number 1 or subset number 1 and subset number 2. Okay, again, MaxMin structure. Alright. And when we have this structure, right, these again, like we have 1, 2, 3, right, basis for quadratics. And then again we have 6 permutations, and we are looking at A, so 6 times A, M, no, actually in this case, and if you remember we introduced lemma, that would allow us to reduce the number of LMIs that we need to look at. And in this case, it says that 2, 3, 1, 2, 3, 1, 3, 2, 1, that one, and then 2, 1, 3, yeah. Instead of having those 3 LMIs, we can have this LMI. So what did we do? Now we have 1, 2, 3, 4. Instead of having 6M, we would have 4M. Yeah, got it. We were able to, like for M. What is M? M denotes the number of subsystems that you have, like A1 dot 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 AM, right? And we would have 4M LMIs to satisfy. All right. Again, like we need to compute that term, right? We need to optimize over like these two terms, and then like constants. We know what A's are, right? Okay. Again, like it will be smart to write AI, right? And then we also have this like P matrices. So many variables, so many matrices to compute. Okay. And again, these matrices will be constant. However, we need to, like, let's say this is yeah. Okay, we can have, let's say, I1, right? And then, or AI. Imagine I did it for all the LMIs, and then we would need to have like one more index for that, because when we have I equals 1 and then I equals 2, for example, we can have, so one more, there needs to be like one more index is what I'm saying. Yeah, it's not like we only have, for example, in this case, how many constants we have? 1, 2, 3, 4, 5, 6, 7. No, that's not the case. We need to have 7 times M constants. Make sense? Okay. For any given A, there exists. So if you give me another A, like I need to have, so I have like more flexibility is what I'm saying, right? Okay, but they stay the same, like P terms. An illustrative example here, and this is the structure that we have, and then A1 and A2 terms, where A2 has a parameter. And when we look at a control upon a function, which was, I think this is like square root of 8 is like 2.82 or something. It's like 5.82. Okay. By the way, of course, I did it before. It's like, yeah, I am not that smart, unfortunately. I'm not a robot. And we were able to prove the stability for, let's say, the range, for this given range of A, right? And this value, this is like 5.82. If we can increase that number, that would be better. Why? Because we would be able to show the stability for a larger set, okay, of parametric uncertainty, which is nice, right? Okay, max of 2 basically is a max of P1 and then P2. Yeah, min of 2. Okay, you can imagine what that is. Quasi-max, I mean, we discussed what that is, right? Quasi-max, quasi-min, max of 3. And if you can see that the number is increasing, for min, it's not the case, but yeah, feasibility of BMIs. What is BMI means? Body mass index. No, that of course that's not the case. This is not gym. This is control. This is like serious stuff, right? We are not like gym teachers. We are control engineers. We are like smart, right? And hopefully we all have also nice bodies. Yeah, I hope so, right? BMI is bilinear matrix inequality, right? What is LMI? Linear matrix inequality. What is BMI now? Bilinear matrix inequality. All right, has been checked. Yeah, with the, what is it? Yeah, Pan BMI is the type of solver that you would have, and it is MATLAB compatible. You would probably use like something like CVXPy or YOLMIP, something like that, right? And yeah, that's it. It also says that it is shown that taking the max of, which is crazy, 7 quadratics. Whoa. Like literally, at this point, if you don't say like, whoa, okay, that means that you don't have any idea. Either you are like a crazy cool person, or you are like, oh, I have, like, you zone out at this point. Why? When we say max of 7 quadratics, and here for this given system, we have like 2 subsystems. We would need to, I'm thinking about MaxMin structure, 2 times 7 factorial. So I computed that it's like 10,000 inequalities, and then these are not like scare these are BMIs, right? By curious, I'm sorry. Okay, I promise I'm not gonna make that short again. Bilinear matrix inequalities, and if you know something about like STPs, they're not as scalable as your like LPs linear programs would be. So yeah, that was, if I am understanding that correctly, that was like a, yeah, quite undertaken. Anyway, so from the bottom of my heart, no, wait a sec, from the LDIs, linear differential equations, now we are looking at more structures type of system. What is it? Switching system. Okay, so again, like, let's focus our attention to those type of, let's look at those functions. All right, the class of switching signals that we consider for system 2 is introducing the following. And first of all, we need to divide the state space. Why? Let's say we have a state space, or rather, yeah, okay, and then we need to say that here, when we are here, the subsystem 1 is active. When we are here, system 2 is active, and here 3. Okay, so some type of partitioning mechanism is required at this stage, and there exists finitely, is the critical word here, many connected sets. And again, like connected set, these are like definitions we will be talking more and more, and then hopefully you get used to that. And connected sets, d1 dot 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 dn, right, described as, and each subset, like J term is defined by with the help of an analytic function. Here S sub J. Okay. Of course, this is the general way of writing it, and then if you can, see the future, if you are like Muad'Dib or something from the Dune MOOC or movie, and instead of having these general structures, we're going to be imposing like more and more like special structures, such as X transpose Q, here in this case J, being positive, like something like that, for example, right? Okay. And here's the thing, and we need to have those sets and correspond, of course, of the functions thereof, and such that the sigma is the mechanism by which you determine for a given x which subsystem is active, right? The which dynamics you are operating under is constant on each dj, and you have like, first of all, because of the way we write, this is inequality, strict inequality. Because of that, this each of those d sub j subsets of the state space is an open set, right? Connected open set. Okay. And then we are taking the closure. Basically, we are including the boundaries, right? And we are taking union. What we need to have is the state space. Okay, we need to be that needs to be a valid partition. Additionally, they shouldn't overlap. Like, these are the constraints, right? Like this is the assumption, and this is the type of partitioning we would need to have. All right, we need to have. All right, and then thus given, we have as again like basis functions, again continuous differential from Rn to Rn. Okay, and we have this switching function, right? Again, like we are looking at one error, right? That means this is a function. This is not set valued map or something. Okay, I'm gonna give you an x, and then you're gonna give me some integer from 1 to m. Okay, this is the deal. We can define a piecewise, like we are going to be defining something just to facilitate. So it's not that critical. We're going to be defining a piecewise locally Lipschitz continuous function, fSW, f switching, and then this is the how we define it. Okay, and then this piecewise locally Lipschitz continuous function. Here's the situation. Now we are going to be talking something about Filippo regularization. I'm almost sure if you read anything about sliding mode control, you have heard about this Filippo regularization. It's like, yeah, I heard about it way back in the day, but at that time I was a poor guy, and then I don't know what economics have to do with it, but I didn't have like a profound mathematical knowledge. So the depth of my mathematical knowledge is, as deep as a typical. Anyway, wait, I was going to make a very terrible joke, but okay, that would even get my channel banned, and I would like to keep my channel. So, all right, let's move on. And Filippo, yeah, at that time I didn't have like math, like at that time, if I saw something like that, I would just scream and then, yeah, run out. Okay, so we define the set, but now I am using ChatGPT basically. All right, instead of screaming. Okay, so Filippo regularization. Here's the situation. Now, instead of having a switch system, we are basically defining. I wouldn't want to say like reducing. It's not making it simpler necessarily, but we are defining another system derived from the original like switch system, and this is the process by which we will be deriving our, or rather basic, using this process, which is Filippo regularization, it is going to help us derive like mathematical sound conditions that we can later impose on the parameters. We're going to be parameterizing our Lyapunov function, of course, and parameters of the Lyapunov function. And again, like one more time, we're going to be turning them into a huge optimization problem. Hopefully, we will be able to solve them, and then we'll call it a day. All right, and okay, so Filippo regularization. We define the set volute Filippo regularization. Okay, let's take this term by term. We have f switching function. Okay, here, like if you see this, if this is the first time that you see this and then you're not like scared, that either you zone out or like you are very cool, you must be Terence Tao or something, I don't know. And in which case, why would you watch my videos? Okay, here's a case. First of all, we have like Lebesgue measure. This is like crazy. I'm not gonna spend too much time on this part. I'm gonna keep it short. Okay, this mu, like measure of this n set, basically measure of this n set, it means that this is the Lebesgue measure of this n sets. Okay. All right, this is something we know, like measure of the n sets such that this is 0. Okay, I can understand that. And first of all, let's try to understand that. We have, you give me an x. All right, let's start there. And then you give me a epsilon. Using that epsilon, I compute. Actually, let me get another color. Using it, that given epsilon, I compute the ball, open ball. All right, and I get rid of some points. Why would I get rid of them? It doesn't say it here, but those are the points that are on the boundary and something, right? The FSV, which was a piecewise, locally Lipschitz continuous function, and where there are some points, like n is a set of points at which FSF is not differentiable, right? We would like to get rid of those points, and then they can be isolated points as well, right? Okay, so for a given x, again, for a given x and for a given epsilon, we construct the open ball, and then we get rid of the points that are not differentiable. So we have a ball, open ball, and then we basically got rid of some points, right? You can kind of, I don't know, like kind of make sense of that expression in your head. Of course, kind of a hand wavy definition or way of explaining things. And here, like where are we? We are in state space, and then using F switching, we from Rn to Rn, we map it to from state space for each point in state space. Using F switching function, we compute a vector. Like for each point in state space, using F switching, we compute a vector, right? That's it. Which is something we would call vector field. Like that's it. I mean, yeah. Okay. And there are some points, however, at which f switching is not differentiable. Okay, so we are not going to be, I mean, this is like a holes, right? From like this is an open ball, and then like red points in this case, and are the points like isolate points, and then where is f switching is not differentiable, and then they are based, if you zoom, they are like holes, but they are just points. Okay, all right, and again like their measure is zero, Lebesgue measure is zero, so it's like kind of you. I mean, I will not go into details of it, but it kind of says that just ignore them or something. When you map these open sets, you will have some isolated points. Okay, so keep that in mind. Okay, and then you take the convex hole and closure. Since we have some isolated points, I am assuming that is the reason why we have this like closure. All right, okay, yeah, this is, and then in the outer part you basically do that for the appropriate n sets and the smallest epsilon, right? Okay, basically it tells us that. Okay, anyway, so where, yeah, we define them, and yeah, we say that this is the Filipov regularization. All right, after this process, we say that x from t to Rn, right, is a Filipov solution of the given system. And here this is, yes, x is absolutely continuous, and for any given t, we have this differential inclusion expression. Okay, here is the thing that kind of got me confused when I first like saw that. I was like, what is this? Like, for almost t, like all t, nothing much. Anyways, like for almost all t, why we need to have that qualifier? Here's the thing. The resulting solution, let's say this is t, and then this is like x1 of t, can be such that, it can be something like this, and at this point you cannot take the derivative, you cannot differentiate it, right? Like, remember, there were some points that f switching was not differentiable, so this is basically the artifact of that, yeah, situation we got over there. And when you have a function like that, you cannot like define the derivative, and then that wouldn't be the case. For example, let's say this is like tx, and for almost all t, like for all t except tx, for example, right? So yeah, that is the reason why we have that qualifier. When you have a system like that you derive using this Filipov regularization process we described, and the resulting solution can have that type of structure where there would be finite, the many and isolated points or time points at which the given solution can be not differentiable. Right. Okay. And hence we have for almost all. Okay. All right. And then let's continue. We're getting very, very close to the end. For the vector field, yes, the computation of if like the sets basically simplifies as observed. Okay, this is a reference and it's somewhere. All right. Consider the vector field. This was a vector field with switching mechanism. We introduce the set volute map J. Okay. So again, like two arrows, we have that set volute map All right. And at this point, for any given like x tilde, this is how we define the sets. And this is kind of confusing. Like when I first saw it, like it kind of like scared me a bit. But let's try to dig deep and explain this. For any given x tilde, all right, and it says that for all epsilon there exists x in the neighborhood, basically in the neighborhood, which is so okay. I mean, this is like, this can be considered as like a cheating code, but this expression basically tells you that like it is the type of stuff that you will see like many times, and then yeah, you can make sense of it that way. That expression basically tells you there exists arbitrarily, there exists x which is arbitrarily close to x tilde. So this is like the English phrase for this expression. There exists x such that there exists x which is arbitrarily close to x tilde. Okay, such that the corresponding subsystem is J. Okay, here we have this state space and this blue dot signifies x tilde. Here this signifies x tilde, and then we have R1, R2, and then R3 regions, and we look at a neighborhood or an open ball, epsilon ball, and then we basically return the active sets. That is it. So it's like, yeah, this is some type of thing that we are familiar with, and so we use that type of function, and this is different than the differential inclusion, right? In the previous differential inclusion, which was general, if you remember, that was fi I is in 1 dot 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 m. Yeah, that was it. This is general. However, like for example, we were basically saying that f1 to dot 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 fm, all of which can be active for any given space, any given point in state space, right? Here we are not basically saying that. We are saying that, you know what, not all the functions will be active everywhere in the state space. We have a partitioning of the state space, and then some functions are active. Rather, only one function, I mean, that's our hope, only one function is active in any sub-region, right? Okay. We have x, again, for a given x, this is set volute map, right? Let's say we have 1 and 3. Then we look at f1 of x, which is Rn, and then f2 of x, and then we look at the convex hull, closed convex hull, which is a set. Yeah, that's it. So these are like the mathematical, I don't know, like technical like steps that we need to take. All right, general stability result. Here's the thing, proposition. Okay, we have the system, and then switching law, we have that switching mechanism sigma. For any given x, it tells you which subsystem is active, and we mention how we divide, how we partition the state space. And let us consider k positive definite continuous differential functions v1 to vk, and okay, they all agree, their zeros agree. If for a max mean function v, okay, where basis functions are given by this v1 to k, and every x, there exists again a class k gamma function, and this is the condition that would allow us to prove the stability, and then v is a Lyapunov function for the system. Okay, so all right, an area. If for a, okay, let's read the expression one more time. If for a given v whose structure is known to us, and every x, there exists gamma of class k function. If we have that condition satisfied, then v is a Lyapunov function. Okay, we're basically saying that, okay, this is like negative definiteness of v quote unquote dots, right? Okay, and for any given x, right, we look at which basis functions, v basis functions, are active, and then for any given x, we look at all the vectors, because this is a set, and set of vectors, and then this vector, and then this is also a vector gradient. That should be the case for all f in the sets, right? Okay, so this is how we would define the Lyapunov function. All right, let's keep on going. So we understand that these conditions ensure convergence to the origin, even in the presence of so-called like sliding motion. And for example, we would have, let's say, system number 1, and then we have system number 2. Like when we have something like that, we would call basically like switching. However, when we have something like, for example, let's say the system is something like that, and then another other system is something like that, then we would have, when we arrive here, we can kind of slide on this boundary, right? This is what we would call like sliding motion, and then we would call this surface a sliding surface or something, or sliding space, and we can a priori rule out the sliding motion. Then we can get rid of some, or rather, when we can a priori rule out the possibility of us having sliding motion, then basically this one, like this constraint, would be conservative. Why? Because we have more information, and yeah, we should take advantage of that, and yeah, that would be conservative. In the next subsection, we propose a stability conditions under this assumption. Right, in this paper it is stated linear switching system with conic regions, and conic regions, that these are the type of like partitioning. Here we are given a set of like QJ matrices, and then they all each of which corresponds to a DJ set, which is a sub-region of a state space. of the space, and this is our system, and then this is the switching mechanism. Then like basis functions, like subsystem, like state matrices corresponding to each subsystem. All right, and then okay, this is the partitioning, and these matrices help us partition the state space, and Qj is symmetric, and then we suppose that no sliding motion occurs along the switching surface. That is a set where, yeah, sigma is not constant, all right? Or rather, I would say sigma is not, we can also say like sigma is not like singleton, all right? In order to provide a MaxMin Liopanov function, homogeneous of degree 2, choose positive definite symmetric matrices, all right, such that resulting MaxMin function is non-differentiable only on the switching surfaces. Here's the critical part. Okay, all right, we have basically, okay, I don't know where to make this point, but this is a very important point. Wait a sec. Here we have our state space. We have sigma, and then that sigma would tell us about the switching, how switching would take place, and then which region of the state space corresponds to which subsystem, right? Okay, for example, this part corresponds to subsystem number 1, 2, and 3. Okay, this is the dynamics, like the system, right? Get another, okay, system, yeah. Additionally, okay, my tablet is being annoying at the moment. Additionally, we also have due to the like piecewise, structure, like this MaxMin structure, we also have another partitioning of the state space. And here's the thing. So in R, V, which takes values from like given K basis functions, takes values from a MaxMin set of MaxMin functions defined by the given K basis functions, and due to like that MaxMin structure, there are some points at which V is not differentiable. Right? Okay, that was the point. And here's the thing, we are saying that, you know what? So some parts of this system, basically looking at that Filippo regularization, there are some parts of the state space, it will not be differentiable. And we are saying that let's choose those basis functions like v1 through that vk, or if we can have like more structure and then make them quadratic, p1 through pk, so that the places where v is not differentiable, like this is a rough way of saying it, coincide with the places where the system, like right hand side, would be not differentiable. Okay, so we basically kill like two birds, right? And I mean, I basically started doing bird stalking, or what was that? Bird pulling? No, bird watching, something like that. And because of that, I kind of don't like this expression now. I try to use it like less and less, but yeah, we see. Yeah, this is how we kill or stalk two birds at the same time. All right, so this comes from the dynamics, and then this comes from basically our Lyapunov structure. Okay, got it. And what was it? Yeah, we have like k functions, and then corresponding to them, since we have k functions, we also have k factor basically permutations, and using each row or each permutation corresponds to a region in the state space. Okay, we have that expression here basically. All right, and all right, yeah. So let's remember what C row was. A row here, J1 dot 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 JK, right? JK rowing. All right. So for a given row, like J1 dot 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 JK, like let's say S vector is okay. For a given row, there is a corresponding J1 dot 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 JK numbers, like in that order, and this is the condition. That's the condition by which you, or rather, wait a sec. This is the condition you would use to see which part of the state space that row corresponds to, right? Okay, got it, yeah. Okay, so we have like region 1, region 2, and region 2, 3, and in each region, we have a specific subsystem is active, and we are dividing this state space so that basically not all but boundaries of the rows, or wait a sec, is that correct way of saying it? Yeah, boundaries, not all of them but some boundaries of the row terms would coincide with the boundaries of the regions, right? Okay, why are we doing this? Because again, like we have a Lyapunov function. Due to its structure, there are some points in this state space, it will not be differentiable. Okay, and we also have a switch system, and due to its structure, like where that switching takes place and stuff, the right hand side will not be differentiable. Okay, and so there are like regions where it is differentiable, and there are regions, or let's say boundaries, where it is not differentiable. So let's try to match the, let's say, set of points where the Lyapunov function is not differentiable, and the set of points where the right hand side of the dynamics not differentiable. So this is like the, in a nutshell, what we have. And let's look at the proposition 3, and then what we have is, let me think about it. Yeah, so we have K matrices. Okay, such that for each, and we have V having that MaxMin of quadratic structure, and for each permutation, all right, there exists a set of numbers such that this condition holds. This inequality condition holds, and for all, like for a given row, that rather one sec, for a given row, immediately you look at C row, right? And in that region, you look at which V functions are active. Like you give me a row, and then from this mechanism, I tell you the active P terms, like active basis, Lyapunov basis functions. Okay, let's say you give me a row, and then let's say we have a 1, A1, A2, or rather, I'm sorry, one sec. Yeah, let's say K equals 3, right? And then, like there will be 6 permutations because of 3 factorial, and 2, 3, 1 would be a permutation, right? Okay, and this permutation, it tells you some part of the state space. Okay, where in that part you can determine which, at this part you can determine which part or due to the structure of the Lyapunov function, which let's say, which basis functions are active, right? And let's say it is a 1 and 3. Okay, then you would do that for that given permutation. So each permutation, like you give me a permutation, there are finite number of permutations, it is easy, and for each permutation, I'm going to give you a set where L will be taking values from that set. So it's basically, what I'm saying, what I'm been trying to say. You give me a row, which is a permutation, which corresponds to a region in the state space, and in that region, due to the structure of the Lyapunov function, we can determine which basis functions are active, and we only look at those basis functions. Like 1 and 3, for example, L equals 1 and then L equals 3. Yeah, this is what we are doing. This is what we are saying here, or that is what they are saying. I didn't write the paper, unfortunately. I'm not that smart. I'm not that cool, unfortunately. But hopefully in the future, there's always hope. And there exist, these constants. And if you can imagine, this comes from like S procedure or S lemma. And I am not proving anything in this paper. Hopefully in the future, I will be going through some of the proofs in this paper. And yes, so this is the situation with the S. All right. And then again, we have for a given row, we have C row, C sub row. Okay, and then C sub row, you pass it through. Considering our switching mechanism, you also determine which subsystem would be active. Yes. For a given row, you also determine which subsystem is active, and then solve that inequality again. Like again, J1, JK, like those things. Like you use them, alright? The only thing that you need here is that row, like that permutation, alright? You look at that inequality, and then that inequality needs to hold for each given row, each given partition of the state space. Basically, is what we're saying. Okay, this is the linear switch system, switching mechanism, partitioning, subsets of the state space, and then corresponding matrices for all permutation. If for all permutation there exists a set of numbers, non-negative numbers, such that this holds where this if we know how to compute that. Yeah, we know how to compute that. You give me that permutation, you gave me the permutation, and then it is like straightforward to compute this f. Yes. And of course there might be another video that I will go through only an example. Okay. And again, for a given row, we have 0, and looking at the structure of the switching mechanism for a given row, how do you find this? How do you find that? Looking at the definition of the switching mechanism, sigma. That is it. All right. And again, this is like S. We have this was the notation. Yeah. Anyway, let's continue. So we have already proved that there. I mean, I didn't prove that, was in the paper. It's stated that way. So we checked some convex Lyapunov functions, and then we checked that there was a. Did I mention the? Okay, wait a sec. Let's imagine we have A1, A2, A3, and then we have Q1, Q2, and then Q3. Right? Using those sets, you determine which subset. Using those Q matrices, you basically partition the state space, and then each subset of the state space, you allocate some subsystem. Okay. So these Q matrices would be your substitute for like, or more structured way of writing sigma, like switching mechanism basically. And we would have P1, P2, and then P3, from which you construct your Lyapunov function. And let's consider that is our structure we impose on the Lyapunov function that we're trying to compute. And when we have that structure, these are the LMI conditions that we need to satisfy, right? So basically, I mean here like P1, P2, and then P3 are mentioned, and then at this point, what we are doing is, so we know what V is, and like P1, P2, P3, and again Q terms, we know what they are, and we are checking if the given Lyapunov function would satisfy the, like, you know, V being positive and then V not being negative, definitely would be a valid Lyapunov function, right? And to do that, we need to look at those given LMIs. All right. Linear matrix inequalities. All right. And now it is linear matrix inequality. Why? Because we know what P terms are. Like we are not optimizing over them. We are optimizing over lambda terms. In fact, this is not even like, is it LMI? Yeah, this is LMI because at the end of the day, this is matrix, and then this is not scalar, like inequality. This is matrix inequality. All right, and so we have P1, P2, and then P3. So K equals 3, right? P1 dot 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 Pk. When we have like 3 P terms, we have 3 times, or 3 factorial equals 6 permutations, and we write them down like one by one, you know, like all those permutations. Okay, and here's the thing: due to the structure of this Lyapunov function, like there is a structure, like we determine, like we decided on a structure, all right, and that allows us to compute which first of all, like for any given permutation corresponds to a region in the state space. And when you have a region, you can also, or rather, is that correct? Wait a sec. For a given, okay, let me take it from the beginning. For a given permutation, you know what that means? This means that, okay, let's try to dissect that. 1, 2, 3. You know what that means? That means we are looking at the state space or part of the state space such that P, like, 1, 2, 3, right? Okay, let's check. Yeah, 1, 2, 3. That means that the points P1, P2, and then P3. And here's the thing. When you have the situation and when you have that structure, all right, first of all, let's look at this expression. Your x terms such that you have this inequality. So which one would get out? Like we have minimum, right? Okay, so this term would get out. Oh, okay. Now we need to look at this term and then this term, and then we return the maximum of it. And looking at the structure, like this is P1 and then this is P3 terms, which one is larger? Which one would be maximum among those two terms? This term. Oh, now I got it. The third, let's say, a basis function of the Lyapunov. Right? Hence, we have that. So this is the procedure by which you conduct that and compute those terms on the right hand side that you see. And I even color coded them because I'm a very thoughtful and polite person. All right, so okay, and we discuss some LMIs, and you basically write them. That is it. Like there's nothing more to that. And when we have, like, when I say P13, we don't, like, I mean P1 minus P3, right? Okay, and then I'm thinking about, yeah. So without doing any thinking, you would write those inequalities. However, there's also, like here, how many? 1, 2, 3, 4. Yeah, we have like 6 inequalities, but here it says that there are 4 inequalities. So that means that we are able to reduce or eliminate, or we're able to obtain a set of LMIs whose cardinality would be smaller than the original one, right? The set that we started with. Okay, so this term, like, let's say this is P1, and then yeah, that one is like the same. It has like the same structure. P2, again, it has the same structure. Now let's look at the terms that contain P3. All right, we need to have 4 inequalities. However, we have 2 inequalities here. So what is the situation here? That inequality we can see here. So that means we have 3 inequalities, and those 3 inequalities correspond to that inequality. Instead of looking at considering these 3 inequalities, we are basically considering only one, which is this inequality. And how we were able to do that reduction, LMI reduction? Okay, I'm just writing those 3 LMIs, right? And from which again, like, this is if and only if. So we are not introducing any type of conservatism, right? Especially we wouldn't want to do that in this climate. Anyway, so after all the random jokes, I am going from here to here, but I am basically not showing that. I can show it, but I'm skipping that, but it is there. So we have if and only if, right? Hence, no conservatism is introduced. Okay, in this video, yeah. All right, and these are the three elements, and okay, I'm looking at this. I am basically, what am I doing? Yeah. So first look at those two, like first and like third one. The outer indices, like 2, right? They are 2s. Or let's look at only like 2, 2, all right, and then 1, 1. Okay, they match. When we have the situation, we can write P32 and then P31 and then inner, right? From inner to inner. P32. Okay. P31 and wait a sec, I'm a little confused right now. I'm sorry. What's going on? Yeah. Okay. P32 here and then P32. Where's 31? That's all right. Wait a sec. Ladies and gentlemen, we are having some technical difficulties. What is this? This is 31, 23, 31. Okay, so I didn't do anything here. I'm looking at those inequalities. All right. And then let's look at inner 31. Okay. And then 32. Oh, all right. Got it. That was okay. Yeah. 31, 32. All right. Okay. So from those two inequalities, we were able to derive that one inequality. And looking at those inequalities, all right, so we have 32 and 23. So basically indices switch. Additionally, on top of that, like the indices agree. So we have lambda 32 and then tau tilde 23, and they are positive numbers. I'm gonna write the same thing, like the same thing here. Basically, I'm gonna divide each constant of each term by lambda sub 32. This is basically what I'm doing. In order to isolate this term, I am doing the same thing. I'm basically dividing each constant by this, coefficient in order to isolate that term. And again, P32, what does it mean? It means P3 minus P2, and then P23 is P2 minus P3. And when we sum them up, we basically have 0, right? And we eliminate that expression. Here, again, we are summing them up, and then what we have is, again, those terms, they agree. We can factorize it. This term, and then, again, these are like the coefficients. Every term here is positive. Because of that, this term is positive, this term is positive, and we can kind of normalize it. And this is what we would have, right? P31, P31, that's it. So this is the explanation and of how we were able to go from those three LMIs to that one LMI. All right, I feel I'm kind of losing my voice. And yeah, I am hoping to maybe make one more video just to focus on a specific problem, to go through like the whole and explain, the algorithm without talking about like the theoretical details. I think that's it, and that's all, folks. Don't forget to like and subscribe. here, this is like the final part. So we have a system where the rate corresponds to system number 1, subsystem number 1, green 2, and blue 3, right? And we wrote down some Liopono function using this MaxMin structure, and we came up with 3 p terms, like p1, p2, p3, and for each, let's say, each region, like given we have 3 regions, and when it is red, v1 is active, green v2, and then blue v3. And here's the situation: they match like exactly, right? So boundaries, or rather, like boundaries imply that v function, the Liopono function that we have, is not differentiable, right? And additionally, boundary of the regions where the specified subsystems are defined, on those boundaries, the system, the right hand side, is not differentiable, and they match, right? So this is something to keep that in mind. And this was the, let's say, success, or how that was possible, because of the way not way, like, because of, yeah, the smart people, some smart people who wrote this paper, and they were able to came up with conditions by which their boundaries, like Liopono, let's say, boundaries, and or the regions where Liopono function is not differentiable, and the set where the right hand side is not differentiable, they will agree. And against, like, the killing 2 birds with 1 stone, yeah, that's it. After stoning a lot of birds, this is what you would have. And I think that's it. Thanks everyone, that's all folks. Okay, don't forget to like and subscribe, and check the description. There will be some information about, like, the maybe GitHub link where you would find some codes, and then the description, or like information about this paper that we went through. It was talking about, like, this non-convex Liopono function and ways to specialize, and then ways to impose some constraints on the parameters, right? And that we introduce on those Liopono functions, right? Don't forget to like and subscribe.